thank you for the kind introduction and the opportunity to give a talk here, and thank you for all of you for being here. I would like to tell you something about the influence of additives on the morphology of gypsum and even the mixtures of additives. And what we did is we first checked, after a short introduction, we first checked the influence of the crystal morphology, the technical properties. Then we checked the influence of single additives and then of mixtures of additives to these properties. So why I had that idea to check that? I started with collecting some gypsum crystals from all over the world, and there are different morphologies given on these pictures and in these crystals all over the world. You have needle-like structures with more or less branches, you have dovetailed twins, and there are very much other ones given in Richter Goldschmidt's Atlas der Kristallform. The book is in German, but it's just pictures, so it's not a problem. Yeah, then we have checked if these morphologies could also be found in technical products, and yes, we could find them in technical products. We have smaller or larger crystals with more or less branches, even dovetailed twins. It sometimes looks very nice. And so the question was, did that influence my technical properties? Did that influence the created gypsum stone? And we checked that with 3 different examples: larger crystals with less branches, shorter crystals with less branches, and larger crystals with much branches. And we checked, for example, the strength, and the bending tensile strength is increasing if you have more branches, and the compressive strength is increasing if you have larger crystals and more branches. And other techniques, other technical properties are influenced too, like the porosity increases if you have more branches or larger crystals. The expansion during hydration is larger if you have more branches and larger crystals. The casting accuracy unfortunately decreases if you have larger crystals. And the compressive and tensile strengths are also increased if you have larger crystals with more branches. And why do we need that information? Yeah, casting accuracy is needed for any casting material. The porosity is influencing the drying process. And even if you have a screed, you want to have a faster drying process. If you have plaster bondage, you want to have any water going out of the material. For ceramic molds, it's influencing the ceramic at the end. Low expansion during hydration is needed for screed or for casting materials nearly everywhere. Therefore, let's have a look how to influence that morphology. We have different ways to do that. We could start up with different raw materials. You could use alpha or beta hemihydrate. In both cases, you could produce them a little bit different. You get different properties. The grinding fineness of the hemihydrate has a large influence. The reaction temperature, additives, and seed crystals are also influencing that stuff. We will go step by step to have a look what happened. And I would like to show you some nice films of, in this case, starting with alpha versus beta hemihydrate. Here we have the beta reacting very fast to thin needle-like crystals, small crystals, and alpha is a little bit slower. It's working for some state stuff like universities like me, so it's a little bit slower. And you get even needle-like structures with more or less branches. And now let's check the influence of temperature to the same product. It's both same alpha hemihydrate, nearly the same reaction speed, but you get other crystal morphology. If you have a higher temperature, 70 degrees, you get very long needle-like structures with less branches. And if you increase the temperature a little more, the film will be boring because nothing will happen. It's roughly 90 degrees, the reaction is completely done, nothing will happen. Now, why is it like that? Let's have a look. Here we have the solubility or calcium concentration or sulfate concentration in solution depending on temperature. And the highest calcium or sulfate concentration you could measure during the time. It's not the solubility, because solubility is in equilibrium and we don't reach an equilibrium because we create dehydrate all the time. So this solubility, solved material, is depending on the type of hemihydrate you're using. Beta has a higher surface, smaller crystals, more cracks, more defects, so you have a faster solving, a higher concentration. Alpha, this time case a suspension autoclave alpha, large crystals, less defects, you have a slower solving of the stuff, and lower concentration. So if you have a lower concentration, the single ions could choose their position on the crystal a little bit more carefully and could create more crystals with less branches, larger crystals, and you have even a longer time solving these crystals. And if you increase the temperature, you decrease the solubility of the solved material again. So you have less seed crystals created here. It's what we've seen. So the complete hemihydrate material is spread to less gypsum crystals which are produced. So you end up with longer crystals and with less branches because you have lower concentration inside of the solution. What I learned through my process here, if you have a higher concentration inside of the solution, you get more branches, and if you have lower, you have less branches every time. So that's one thing which is really influencing my morphology. So how could I check, how could I get information about this concentration inside of the solution? That's a little tricky. Different of the techniques possible. You could use ion chromatography. With disadvantage, you have to filter and dilute your solution. And especially at the beginning, there are some small crystals which could pass the filter. And then you dilute your stuff and you solve them. So you get a higher concentration compared to the one which is really inside of the solution. But you get also information about other ions inside of it, like sodium, potassium, and whatever. So it's sometimes important to do that. With a calcium-sensitive electrode, you get direct information of the calcium concentration, but only calcium in the solution. That's a good technique for getting some information. And if you want to have something cheap and easy, you could even measure conductivity. But it's an integral method. It gives you information which includes every ion which is inside, but you could not say how large is the influence of one special ion. So it's a cheap technique which gives you more or less the same result, but not perfectly, always. So let's check how such a result looks like. Here we have the increase of concentration of calcium in the solution because of the solving of hemihydrate. And you have the creation of seed crystals, and they start to grow. And here in this part, you have as much hemihydrate solved as you need for the growing of the gypsum crystal. It's more or less in equilibrium. And now most of the hemihydrate is solved, and I could not deliver so much ions than I need for the crystallization of dehydrate. So concentration gets lower and lower until hemihydrate is nearly completely gone. And it will stop around the solubility of dehydrate. You will not reach zero. Now let's check what happened if we put some other things inside of our solution. If you add some potassium sulfate, any calcium ion will be collected by the sulfate ions in the solution and create gypsum, so the reached concentration is a little bit lower and gets lower faster because you have sulfur ions inside of the solution. But what will happen if you add citric acid? It's really interesting. You keep the calcium concentration longer inside of the solution. I expect that the citric acid collects calcium ions first, and then when you reach the seeding process, and if you have gypsum crystals, the citric acid chooses to be on the gypsum crystal and gives the calcium ion free for the solution again. It's the reason why I keep that concentration higher here. And same effect if you add some potassium sulfate, you have a lower concentration because sulfate is collecting some of these calcium ions. How does it influence the morphology of my gypsum crystal? Let's start with pure alkali sulfates. With pure alkali sulfates, I get needle-like crystals with less branches. If I add potassium sulfate or lithium sulfate, whatever. I think the reason is you could first create sulfur chains in the solution, and then you add calcium ions to that, and then you have a backbone which could grow. And the reaction is much faster. All of you know potassium sulfate is an accelerator which works very fine. Now let's have a look to pure material reacting again, and we compare it later to something else. Here we have alpha calcium sulfate hemihydrate reacting with water. You see why we have expansion during hydration, the crystals pushing each other away from the next one. So we have this expansion, we have the creation of a network of gypsum crystals with more or less branches in this case, and even some dovetail twins could be seen here. Now this video is free for download with some documentation in German or English on our homepage, so if you're interested, it's free for use. And the crystals are looking like that here. A mixture of longer and shorter crystals with some dovetail twins. And now we add a little citric acid, just a very little amount. And we end up with totally different morphology. 0.25% is, if you see that on the table, it's nearly nothing. You got shorter crystals with a larger diameter because citric acid lights this surface of the gypsum crystal, and it blocks that from growing, and the other ones are more or less free of citric acid. I checked that with micro-Raman spectroscopy and AFM. Citric acid in lower concentrations could only be found on the C-axis, on this point of the gypsum crystal. So it stops the fastest growing surface from growing. And so we got a wider crystal with less branches. And here you could see that again, we have shorter crystals with less branches, the 240 minutes. Now let's add a little bit gypsum, accelerated, dehydrated crystals, 10%. Let's check what happened now. We have these gypsum crystals here inside, they are still growing, and we have a seeding of gypsum crystals, small crystals out of a solution. So we end up with a mixture of larger and shorter crystals. And that we could choose a little bit the particle size distributions of both, depending on the amount of dehydrate we give in, the particle size of dehydrate we give in, and therefore we got maybe a better mixture, better technical properties of our materials just by changing the material we are using. And yeah, here I have 10% because I want to see something. It starts with lower amounts also. You could use lower amounts and you get a faster hydration too. And here you see that, large crystals and some smaller crystals which are created out of the solution, and these are the ones which are inside before. How about mixture of seed crystals and citric acid? Now let's check first the hydration of energy of this step, and we will step by step add some additives. Here we have a pure calcium sulfate hemihydrate reacting with water. We have solving of hemihydrate, creation of seed crystals. Now the seeds start to grow, and hemihydrate is still solved. And now I could not deliver as much ions as I like to have for the growing of gypsum crystals because hemihydrate is mostly solved. I get less energy, and at the end my reaction is done and everything's completely reacted to dehydrate if I'm lucky. Now I add some citric acid. Disadvantage one is I get lower strengths with citric acid because crystals are shorter and I have less branches, which is not so good for the strength of my material. And I get an increase of this period where the seed crystal formation takes place, I think because I bound calcium ions in the citric acid. And then I have some seeds, and citric acid step by step go on these seeds. And I have a slower growing, I have a wider peak here, because the fastest growing surface is poisoned by the citric acid. And therefore I get a wider peak. Now it would be interesting to have dehydrate inside. If I have dehydrate small amounts inside, I have no period of seeding here which I could measure because there are some crystals there, and depending on the amount of dehydrate I add, I have a faster growing of the peak here or a slower growing of the peak, and I shifted to a shorter hydration time. And what's interesting, if I add just maximum 5% of dehydrate, I get better strengths. If I add more, somewhere I get less strength. So it makes sense, it not make sense to add so much dehydrate, but nobody will do that because material will go too fast. We could check that here. I have done mixtures with more or less hemihydrate inside of my dehydrate inside of my hemihydrate. This is a pure one, 0.1% of dehydrate. In this case has nearly no influence. But I also checked the particle size distribution of hemihydrate and dehydrate has an influence to that. So if you have a finer dehydrate, you need less material. It's just a question of amount of seeds. And if you increase the amount of dehydrated material, it gets faster and faster, and at roughly 1 or 2%, you have nearly none of this seeding process anymore here, and then you have a very fast reaction at higher concentrations. If we have a mixture, which is typical, we have this making faster with by dehydrate and slower by citric acid, we could end up with a material that is more or less the same hydration speed like the pure material, just by retarder and accelerator mixing. But what does that mean to our morphology? Let's have a look. Here we have the mixture of citric acid and dehydrate in one solution, and we will check what will happen. Here we have the dehydrate crystal, which are still growing, but with a morphology of typical citric acid on top. It's this blocky structure, and we have new smaller crystals created, which also have this structure, typically influenced by citric acid. If you use a higher pH value, you could also use tartaric acid, apple acid, or whatever. Here we have that, larger crystals with this typical morphology, and they should look like before. And here we have the smaller crystals with this typical morphology. So citric acid is influencing very much. Now let's have a look to the mixture of citric acid and potassium sulfate. Pure potassium sulfate leads to finer crystals, longer needle-like crystals, and with citric acid wins. And you get the typical morphology of citric acid, even with a very small amount. And now let's have a look to the mixture of all this stuff. Here we have the pure material, and here with some dehydrate, with the smaller and larger crystals. And if you compare these larger crystals, the same dehydrate I've used here with the citric acid, I get this typical morphology change. And even larger and smaller crystals too. If I add only citric acid, I have this typical blocky structure. With potassium sulfate in longer crystals. And if I use citric acid and potassium sulfate, as I show you, I have this mixture of shorter crystals with large diameter. Citric acid is mainly influencing the morphology. And with dehydrate and calcium sulfate, I get larger crystals of dehydrate before and needle-like structures of the hemihydrate like we expected. And I have the complete mixture. I get larger crystals and smaller crystals, more or less comparable to that one, but it's a little bit finer because of the potassium sulfate. And I think it's one key to produce better products if you have a good mixture of larger and smaller crystals. And maybe you could even influence the morphology of the dehydrate or the new created seed crystals to get a perfect mixture with perfect properties. And that's the key to do that is mainly optical microscopy or SEM or whatever. Just the morphology of the crystals are very, very interesting to get information about the products. So let's come to a short conclusion. Hydration of hemihydrate is the process of solving and creation of supersaturated solution. And then we have the creation of seed crystals and the growing out of the solution. And still hemihydrate is solved during that. And the degree of supersaturation is influenced by the solving speed of the hemihydrate, and it's influencing mainly the morphology of the seed crystals you're creating. And for case of beta hemihydrate, it's faster than for alpha, and supersaturating is regulating the complete seeding process and the morphology and everything else. So to understand that step is one of the keys to get better products. Citric acid, as you all know, retards hemihydrate, and you get the fastest growing surface inhibited from growing, so we have a wider peak because the other ones are growing slower. The strength of gypsum stone gets lower with citric acid a little. Potassium sulfate leads to longer crystal needles as a higher temperature do, and you have less branches on the stuff, and the reaction is accelerated. Small amounts of dehydrate also increase the hydration speed, and small amounts really increase the strength of the material. And larger amounts of dehydrate is decreasing the strength of the material, unfortunately. And a high reaction temperature also leads to longer gypsum crystals with less branches. Risky. Different gypsum morphologies can be found in nature and in morphologies in technical gypsum-based materials. The morphology of gypsum crystals is influencing different technical properties, and nearly every additive is influencing this morphology, which is created during the hydration process. And even if you have mixtures of additives, they are working against each other. So with this easy technique, you could check if it works together or not. So optical microscopy is a powerful tool to get some information about that. And with optical microscopy, it should have some help by other methods, but you could get some information about better or less strengths or better or less technical properties, and even a little bit about hydration speed could be estimated. But you should support that by calcium-sensitive electrode to get some information about the liquid phase, or you could add some information about calorimetry or temperature thermometer measurement, where you could get some information about the hydration speed. And the gypsum morphology could also be investigated very nicely with SEM or ESEM. And to the end of my presentation, I would like to show you what gypsum crystal is doing when you get some stress. Of course, less stress than I gave you here. We have this crystal and a 3-point bending test, and it starts to bend. And this step is reversible. If you turn it around and put pressure from the other side, you end up with a flat surface again. But it just works in one direction, directly orthogonal to the cleavage plans. Here you have the cleavage plans of the crystals. And that bends a little bit more, but I don't want to bore you with that stuff, so maybe I could skip part of this video. You end up with a U of the material at the end. And yeah, with some nice pictures of my work, I would like to say thank you. Here we have gypsum crystal with SEM, here polarization light microscopy of a nice gypsum crystal. Here we have portlandite with SEM and some cement clinker, also with optical microscopy. I sometimes detect some clinker phases when I have some time. And with that, I would like to say thank you for your attention. And with this transparency, thank you for listening, but this transparency is stolen, it's Rob's. So, thank you very much.
Thank you very much indeed, Christian, for a breakneck overview of the influence of on crystal morphology. Thank you very much indeed. We have a number of questions that have come in. I think the most important one is, do you think that the observations of crystal morphology that you detected in low-speed reactions can be considered valid in very quick conditions such as plasterboard?
I did the same stuff with beta hemihydrate, and you see more or less the same stuff, same morphologies. If you take, for example, a hydrated system, and you search for these gypsum crystals, for example, this seed crystals, you will find them even in the hydrated system. You will find more or less the same morphologies even in these systems. We did much tests for that. Yes, I think so.
Okay. Next question. Did you observe any effect of potassium sulfate on the compressive strength of the affected crystal structures?
Yeah, it has a small influence, but it's not so large like in case of the citric acid, because the particles get a little bit larger, so the space in between is a little bit larger, which may influence even the compressive and tensile strength a little bit.
Okay. I've asked at higher ionic concentrations, are there automatically more nucleation centers? So really what I'm asking is what causes something to become a nucleation center?
Yeah, it's a question. If you have more ions in solution, you have to find perfectly fitting calcium and sulfur ions together as a special morphology at the beginning of the seed. And if you have more ions in solution, you have a higher chance. And if you increase the calcium amount in the solution, as far as I observed now, you get more branches. If you have more sulfur in the solution, you get more needle-like structures. I expect if you have sulfur, you get a chain of sulfur ions first, and then the calcium ions will go to the special places. If you have just both in higher concentration or more calcium, you have just one sulfur ion and it fits with some calcium around it. And therefore you get also different of the seeding process, just by having more or less concentration of one of the ions.
Okay, but just to go back a couple of steps there, is the fact that something becomes a nucleation center, is it because the ions have just fitted together momentarily in the correct orientation, and then from there other ions come and build onto it to make a crystal?
Yes, I think so, but you have to have a critical surface of it, you have to get that, otherwise it will also get solved somewhere. But if you get the critical mass, you will have a seed which is growing. But I also checked the influence of different things which could work as a seed. I checked barium sulfate, potassium sulfates, sand, dozens of substances, and nearly nothing works. Just dehydrate really works. Anhydrate also not working.
Okay. Another question. It appears that the optical microscopy results that you've presented are actually based on alpha gypsum. How do you think that the results would change with beta gypsum plasterboard?
Yeah, I checked also with beta hemihydrate, and you get not for every additive. Some additives are not really working as well with beta like with alpha, but in most cases you get the same results. But I did not show you because beta hemihydrate, you see, it's very, very fast. In case of alpha, it's even better visible because you have more time. Video has more time to change something, and the change will be more obvious just because it's slower. But you will get more or less the same results in most cases just for beta.
Okay, what is the best crystal morphology to have the most resistant crystal network?
For what? For what technical property?
Giacomo Lamoro, please complete your question. Where are you?
You see that it's possible to have different morphology.
Yeah.
For instance, fibers, almost
Yeah,
other kind of shape.
Yeah.
What is, in your opinion, the best shape to have the best network resistance?
For the best network, just for the best strengths, I think you need much branches and large crystals. But on the other hand, if you want to have a higher water resistance, for example, you have to have a dense structure. You even reach a dense structure with smaller crystals, with less branches. So it depends what you want to do. Any technical property has a special morphology you need. If you take technical products and you check the morphologies, you will see that they are typical for special things you're using your gypsum material. If you use, for example, casting materials for dental castings, they always have small crystals with less branches because they are interested in good casting accuracy. If you have plaster bondage, normally you have larger crystals with large branches because you need the porosity to get sweat out of the stuff. So it depends what you want to do.
Okay, that's another one for the coffee break. Thank you very much indeed, Giacomo. Very final question. Are you going to continue your research in this area, and what will you investigate next?
Yeah, it's just starting. We did other mixtures of additives where we are interested in. We get information about when to add these additives and how it changes these additives to other times. We checked different types of hemihydrate. It was just small amounts. We did very, very much other things, and we are doing still other things.
There's still a lot to research out there.
You have a large field you have to do for the next years. It's not a problem.